Okay, so now we're going to talk about the next kind of surface, which are hyperboloids of one sheet. And this occurs when we've got something like x squared over a squared plus y squared over b squared minus z squared over c squared equal to 1. The important thing really is that these guys have positive coefficients x and y. Z has a negative coefficient, and their sum is equal to a positive number. And the shape we get here is really sort of reminiscent of a cooling tower. If you think of a cooling tower from like a nuclear power plant, it looks something like that. And so that's what this busy diagram over here is supposed to suggest. So let's look at x squared plus y squared minus z squared equal to 1. If we set either of x or y equal to a constant k, we get the other guy squared minus z squared is equal to 1 minus k squared. Now if k squared is not equal to 1, then we get a hyperbola. And we either get hyperbolas that are opening sort of are sort of two vertically aligned pieces or two horizontally aligned pieces. And it just depends upon whether k squared is less than 1, which gives us these more vertically aligned guys, like this red guy here, or if k squared is greater than 1, we get these more horizontally aligned type guys. All right, and so our vertical slices in both the x direction and the y direction give us hyperbolas, lines. In the z direction, when I let z be equal to k, I get x squared plus y squared is 1 plus k squared. That's an ellipse. No matter what k is, this is just going to be an ellipse. And specifically here, it's a circle. But anyways, so my traces in the z direction are these circles. And here I've really tried to illustrate all of the different possibilities for the sorts of hyperbolas you can get. So in the x direction, hopefully you see I've got a one sort of hyperbola here, the vertically sort of aligned hyperbolas. The two sort of vertical pieces. I've got this sort of hyperbola here, which are the two sort of horizontal pieces. Then right here I have a picture of the two lines. And yeah. Great. Again, just for good practice, let's draw the traces for this one-sheeted hyperboloid. X squared plus y squared minus z squared equal to 1. And I've given you some suggestions for the traces you could use. X and y, let them be 0, plus or minus 4/5, plus or minus 1, plus or minus 5/4, because those make the math work out nicely, just believe me. And for z, let them be 0, plus or minus 3/4, and plus or minus 4/3, and just see what the traces look like. Alright, so you may have wondered why we had something called a hyperboloid of one sheet. And that's because we have something called a hyperboloid of two sheets. This occurs when we've got x squared over a squared plus y squared over b squared minus z squared over c squared equal to negative 1. So really, positive, negative is equal to a negative number. And that's what's going on here. So for example, let's look at x squared plus y squared minus z squared is equal to negative 1. I mean, really, this equation, I just drew this picture independent of the equation. This is really not this exact equation. So, yeah, I lied. Oh no. So let's look at the traces. Let x, y, and z each be equal to a constant. And the math goes pretty much just like last time. We end up with hyperbolas for x and y and ellipses for z, but it's a little bit different. Y squared minus z squared is minus 1 minus k squared when x is equal to k. So this is always less than 0. In that case, we get these hyperbolas, which are, sort of two pieces, one over the other. And same thing for when y is equal to k. So these traces are always disconnected. In the x direction, it's always disconnected, and the y direction is always disconnected. So there's no way that this surface could consist of one connected piece. It has two pieces, two sheets. Great. So that's what's going on here. That also means that a bunch of these horizontal slices, the z slices, have to be empty. And let's see what happens there. X squared plus y squared is equal to k squared minus 1 when z is equal to a constant k. So we get ellipses when k is greater than or equal to 1. And when k is equal to 1, we really just get 2 points here and here. But when k has absolute value greater than 1, we get elliptical cross sections like this. Cones are the last thing to look at. This occurs when we've got x squared over a squared plus y squared over b squared minus z squared over c squared is equal to 0. So really plus plus minus is 0. What we get here are two cones with their tips touching. This is really the analog of the two lines, the conic section, which looks like two lines. So for example, let's look at x squared over 4 plus y squared over 9 minus z squared equal to 0. And you know what? For question 4, why don't you try sketching the graph of this? Really, all I mean is place this in on a three-dimensional axis and sort of sketch some of the traces. That's pretty much it. And yeah, great. Go ahead.